Okay, so having introduced the CMY model, let's uh, let's look at how we convert from RGB to CMY. So CMY is subtractive and RGB is additive, and so it's quite intuitive that actually the way we get from RGB to CMY is to simply subtract the RG and B values as a vector from the vector 1, 1, 1. Um, so the assumption there is that all the RGB values lie in the RGB color cube. So that's the conversion, which is our first example of using or treating RGB really as a vector in order to, and then performing some sort of operation on the vector to transform it from one color space into another. So this is a linear operation. The next model that I'd like to mention is actually there for historic reasons, but it's one step up in conversion complexity. The reason that I mention it is it is interesting because it 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 includes an aspect in which a color space model can reside alongside a model that serves to represent or provide an image for uh, an achromatic image or grayscale image. So the YIQ model has been widely used in analog color TV broadcasting. So in the early days of television broadcasting, the early televisions were achromatic or black and white, not really black and white, but really grayscale. So they're achromatic, and the introduction of color television was presented a technical challenge, and the solution to this was, in order to maintain compatibility with black and white televisions, was to introduce two color channels, um, which are in or two color channels, yes, which are encoded in the Y and the I and the Q signals. I and Q don't really stand for the usual or any usual color sort of information. They encode color information, but instead they are named after in phase and quadrature signals within the transmission. So if you've done any communications theory involving radio broadcast or if you've done signal processing or ultrasonic imaging or indeed MR imaging, you might have come across the idea of in phase and quadrature signals. And so in this case, the in phase and quadrature signals encoded the color information, whereas the Y included the the intensity information, and that was compatible with black and white televisions or monochromatic televisions. So you could have color broadcasts without breaking the people who had the utility of the broadcast for people who only had black and white televisions. So the conversion is interesting again. It's one step up in complexity, as I said, because what you now do is you multiply RGB as a vector by a 3 by 3 matrix, which transforms this vector into YIQ. Now, there is probably some sort of geometric interpretation of this, but it's not something that's discussed very much or expressed very much. So we're not gonna spend time on this, but it does suggest the use of again using RGB as a vector and then operating on that vector. Okay, so I've really included this for academic interest, but there is a stark contrast between the color space that we have here in YIQ and also in CMY and HSI or HSV color spaces, which are more commonly used in the field of computer vision and also in pattern recognition. So if you need to recognize objects of a certain color, you're more likely to use HSI or HSL color space or something similar. So these are the color spaces that we're going to now explore are so-called perceptual color spaces because they are more aligned with the way that human vision works and human intuition works around color. In that sense, they are also more closely allied to normalized RGB that we introduced earlier on. Okay, so the HSI color space decouples the color information from the luminance information. So in that sense, it's a little bit like the YIQ color space. But instead, there's a very precise, well, in fact, there are many definitions of the terms hue and saturation within this color space. And this seems to be more closely aligned with the way that human perception of color works. Now, I'm going to start off by looking at a simple HSI geometric model. And so, if you remember, we had the RGB color space, red, green, and blue. And red, green, and blue turn out to be so pure high intensity red is ends up as at one of these vertices of this two pyramid. This is one pyramid stacked on top of an inverted pyramid. The pyramids have triangular bases as opposed to square or circular bases. Well, that's important, as we'll see later on. But the color space can be thought of like this. So the notion of hue effectively specifies a color, and it effectively specifies. So if you think about some sort of color, again as a vector somewhere in this, first of all in the plane of the base of these two pyramids where they touch each other. So we're just looking at this slice of this three-dimensional space. If you grab the if you have a point that lies in this plane, and it's denoted by the point P, and that represents a color, then the hue associated with that color, it tells you about the angle that that vector describing the location of P makes with the red axis. So as hue increases from 0 up to a full rotation, you're effectively moving, so 360, you're effectively moving around this, the center of this this plane. The saturation, which is the other important measure here, is actually, so 1 minus saturation gives you the distance of this point, so the length of this vector here. So when we get to full saturation, we are saturation represents, so S represents, which is saturation, represents the length of this vector here. So when we get to full saturation, we have solid colors of full intensity red, or full intensity green, or full intensity blue. As saturation decreases, so as saturation tends towards 0, the length of this vector changes, and the amount of the color we have within the within or the amount of the a dominant color within the color that we're talking about. Sorry, this is I'm talking in what do you call it? So my description is becoming a circular reference, a circular definition. So let me start this again. So let's say that we have some color that we define by the location P. Okay, the saturation is an indication of the length of this vector from the origin of this triangle, so the center of this triangle, to the location P. As S, the saturation value, tends towards its biggest value, we push P out towards being what we call pure saturated colors. As P gets closer towards the center of this triangle, then we have decreasing saturation to the point that when S actually becomes 0, that point P lies on the middle of this, or at the center of this triangle. And when that point P is on the center of this triangle, we are actually lying somewhere along the R equals G equals B line of RGB color space. In other words, if we were to take RGB color space and find the line between 0, 0, 0 and 1, 1, 1, which is the line containing grayscale information, that is, it's effectively white light, so there's no dominant color, that is increasing in intensity between 0, 0, 0 to 1, 1, 1, then we are moving in this color space, HSI color space, from this point on the pyramid, which is pure black with R equals B equals G equals 0, up to R equals B equals G equals 1. Okay, so grayscale effectively lies along the midpoint through here. So what's going on here? So way of thinking about this is that if I take let's say that I have I start off in red, green, blue color space. If I want to, and I have R equal to 0.33, okay, so one third of the way between 0 and 0 and 1, and I have 0 for green and 0 for blue, then what I have is a fully saturated red value, but which is of 1/3 intensity. Okay, so there you see that we've incorporated the notion of hue, which is red. We've incorporated the notion of intensity, which is 1/3, and we've incorporated the notion of saturation, which is full. So it's full saturation. That means that we have no extra grayscale included in that. If we want let's say achromatic intensity included in that. If we were to take that away from being fully saturated, then the way that we would achieve that is by taking a low intensity quantity of achromatic light. For example, we might take R equals 0.1, G equals 0.1, and B equals 0.1. Okay, so they're equal and they're 1/10 full intensity, so it's kind of a very dark shade of gray. And you then blend that in. You can even do it additively in this. This is just a sort of vague illustration. You can add that in to, or you can add the red into that, your 0.33 of red into that. So if you did that, you would have your red value being at 0.1 plus 0.33, which is 0.43. Your green value would still be at 0.1, and your blue value would be at 0.1. So that would be an example of a case in which you no longer had something that was fully saturated. You were instead somewhere lying towards, you'd push the value somewhere towards the center of the pyramid, and also you would still be moving though along the red line, because we haven't got any other dominant color. We've not shifted away from the red angle, so the hue angle would still be 0, corresponding to just pure red blended in to R equals 0.1, B equals 0.1, G equals 0.1, therefore a bit of gray. Okay, so that's the way that I tend to think about this. Now, one question you may want to ask yourself is, if you had such a color, where does that lie on the HSI bipyramidal cube? Okay, so I leave that to you as an exercise to think about. One of the ways of doing it is running that example I gave you through an RGB to HSI or HSL converter, and then see what values pop out. So you may want to try doing that, and I suggest you do that. If you are doing it, do it in the practical. So I'm hoping that what you do is you start working on the practical, you understand how to access some of the functions, and then you can actually come back to this lecture and try to do that, to see where that value of 0.43, 0.1, 0.1 would lie in HSI color space. Okay, so yeah, I think that's all I wanted to say about that. So let's move on. So next, we're going to talk about how we represent on paper a continuous field of intensity and how we might represent a continuous field of color.